Welcome to this mini lecture on neural networks and their application to media data. So in the first part of this lecture, we're going to go through the basics of what makes a neural network. Neural networks are comprised of a basic unit called a perceptron. What a perceptron does is take inputs in the form of data, raw numbers, and process those inputs into later layers of our neural network. The best way and easiest way I can think about explaining what a perceptron does is to go back to some basic maths. So I think most people would know that if I take the number 1 plus number 2, that would actually give me 3 as an output. A perceptron does this kind of arithmetic within its internal functions. The way that we actually draw a perceptron is using usually a circle, and this circle has inputs with some output on the side. In this particular case here, the plus sign refers to what's inside this perceptron, what we call the internal activation. So in this case, if I was to convert what is a very simple equation into a component of a neural network, then I could do this quite easily by just saying 1, 2. The internals of this neural network then would take these inputs, sum them, to produce the output 3. Taking this one step further, with some neural networks, what we actually do is rather than just allowing the sum of whatever inputs come through it to feed directly into the output, we actually modify this component at this point. So whatever sum comes through from these inputs is then turned into and transformed using what we call a sigmoid or a tan H function. So these usually look like that small symbol there. Essentially what these functions are doing is taking a range of inputs and squashing them down to a set range, perhaps between +1 and -1, or +1 and 0. What you're trying to do is stop the outputs of these perceptrons becoming too large. So now that we've converted our individual equation here into a single perceptron, let's make some other modifications to our equation to make this a bit more realistic to what a neural network actually is. So one of the first things that we have to do is actually add a couple of other components to these inputs. On a perceptron, rather than these values that we're feeding in directly going through the perceptron, we actually modify these according to what we call weights. So this one I'm going to call W1, and this one I'm going to call W2, weight 1 and weight 2. Up here, my equation I now have to modify by adding these weight components as multipliers. So if I take this equation at the top, I take 1 and multiply it by the value at W1, and then add it using that internal activation to 2 multiplied by W2. If I put these in brackets, it makes it a little bit easier to see how these particular values feed through. Now in this particular instance here, we're no longer just getting an output of 3. We're getting an output that is determined by the value of these weights. And this is where we start to actually add some advanced calculus and some advanced functionality to our neural network, because now all of a sudden, if we modify these weights, we're going to have control over whatever comes at this output here. So in the first instance, let's just initialize our weights, each of them to 1. So let's say W1 equals 1 and W2 equals 2. W2 equals 1 as well. In that case, we get exactly the same output we had before. We get 3 at the output here. But you notice that this gives us an ability now to actually modify this aspect. So if I actually had, instead of W2 here being at 1, if I now instead made this weight 0.5, then it means that the output here is no longer 3, it's actually 2. Because I'm effectively halving this 2 coming through and diminishing its contribution to the output.